So these are some things I like thinking about. They all have a common theme, but it's hard to state it in a sentence. But basically, I like things that use two of the three words: random, ergodic, and hyperbolic. So choose any two of those three. That's awesome. So like connections between algebraic properties of groups and behavior of random walks of them. So the simplest case is the first, we take a random walk on a two-dimensional thing. You'll come back to the probability one, and if you take it in a three-dimensional thing, you won't. It's a lot complicated. So like asymptotic properties of random row groups, connections between probabilistic geometric boundaries, relations between random walks and dynamics of geodesic flows, and well, the topic I will discuss kind of at length now, invariant and stationary random subgroups and interactions with other things. So all of these topics have many interesting and accessible problems. I will mention a few. And okay, if you Google any of these things that they look cool, you should talk to me because I can only mention so much in 15 minutes. So this is like a subject I've been thinking about recently. So suppose you have a probability measure preserving action of some group on some measure space, and we're interested in studying the stabilizer of typical points. So, okay, so maybe in this generality, you imagine it's hard to say anything, but in fact, when G is a simple Lie group of rank at least 2, like SL and R, or N at least 3, or a lattice in such a group, which means that the quotient has a cofinite Haar measure. Stuk and Zimmer proved a very strong rigidity theorem, which means the stabilizer is very small, the identity, or very big. So a lattice in the group means a large discrete group. So this is a strong statement that you can actually, if I had half an hour instead of 15 minutes, I could like talk about how to derive Margulis's normal subgroup theorem. It says if you have a lattice in H3 or lattice in like SLN or N at least 3, then normal subgroup of that has to be finite index. So okay, that means it's probably something hard, and it's spectacularly false if your Lie group has rank 1, like SL2R, and you can talk for years about like all the exciting ways in which it's false, but still, you want something. So in that spirit, myself and Ilya proved a few years ago that a weaker statement with the same philosophy is true. So if you have a measure preserving action of SL2R, almost every stabilizer is either a point or it's a big discrete group. So to talk about what I mean by big, I have to talk about a notional size of a group called the critical exponent. So so the G be a rank 1 Lie group, and you can just think of SL2R. Z is its symmetric space, which you can think of as H2. So which means it's a metric space, and it sort of it's a negatively curved manifold. You can say lots of things about it. So the critical exponent of the action or exponential growth rate of the action is the following thing. So you take a subgroup, hopefully you choose a discrete one. You look at the number of orbit points in a ball of radius r. So by how negative curvature works, as the ball grows, this number of orbit points grows exponentially. So you take the log, you divide by, it should say r to r inverse, r to the -1 instead of n to the -1. And take the limit. It turns out always to exist. Okay. So when H is a lattice in G, so this number, has a lot of geometric meaning. So for each symmetric space, it's sort of determined by these values. For hyperbolic 2 space, it's 1. You can also think about it as the Hausdorff dimension of the boundary of the symmetric space in the right sense. And so this number is the maximal possible sort of exponential growth rate of a discrete subgroup of G. Lattices are the biggest possible discrete subgroups, and we can denote it by something. So it depends only on the group. The theorem with RULV, if you have a measure preserved reaction of a rank only group or a lattice in such a group, so a lattice, for example, this would be SO2Z. Almost surely the stabilizer is either the identity or a discrete group, which is not quite as big as a lattice, but it's still pretty big. Like the critical exponent is more than half the maximal thing. So that's rank only groups. Well, maybe there's not that many of them. It also implies for probability measure preserved reactions of any elementary means doesn't have a finite big subgroup isomorphic to Z hyperbolic group, where the critical exponent, so these balls are taken with respect to the action on its Cayley graph. So a hyperbolic group, for example, you could have still a surface group, or you could have a free group, or a fundamental group of a negatively curved manifold, and a Cayley graph gives symmetric on it, and you can take this critical exponent. Okay, so that's fine. The proofs are kind of complicated, and you use some generalization of the Birkhoff-Rogatic theorem, but for big groups that are, if you take averages over orbits of balls, they converge to space average. And these are hard to generalize. I mean, it would be great, but if any of you could, but I don't suggest it as a master's problem. Unless you're, unless you're a gambler. Okay, so, but it is an interesting story to generalize all these things beyond hyperbolic groups, and without using this kind of horrible ergodic theorems, which are super complicated. So a nice generalization of hyperbolic groups is something called relatively hyperbolic groups. So example of relatively hyperbolic groups. And by the way, this is something that there's like 20 people in this department who will tell you about and they're excited about. So examples are non-uniform lattices in HN, or in negatively curved manifolds. So it's an isometry group such that if you quotient it out, the quotient has finite volume but is not compact. And free products of arbitrary groups. So maybe you have a bunch of groups, A, B, C. You take A, free product B, free product C. So that's how the hyperbolic. and these are generalization of free groups. So, free groups are hyperbolic, free products are relatively hyperbolic. Okay, I'm not going to say much more about this. Okay, and you want to prove the same thing, that maybe for a larger class of groups, almost every stabilizer is either the identity or a subgroup, or it's very big. So maybe the same result as critical exponent, at least more than half, like the critical exponent of the whole group. Okay, and the approach that I sort of come up to this problem, of course, I haven't carried it out in laboratory reality, is that you can solve this problem studying like measures, studying actions which are not measure preserving, but something called stationary. So what does it mean to be stationary with respect to some measures on G? So it's stationary for, okay, so you have a measure in G, and you have a measure on the space X at Xi, and it's stationary. It should say, so this convolution is the definition. So some G mu of G inverse of A. So stationary. So mu stationary if mu star B is equal to mu. So intuitively, what does it mean? So if you choose a point in X, distributed according to the measure mu, and you apply one step of the Markov chain on G, where the probability of going, of multiplying by some element each step is the measure assigned to this element per mu. So whose jumps are below mu. So then the law of the mu point is mu star B, and the mu stationary probabilities are the laws which are invariant under the random walk. Okay, so what does it have to do with anything? So 2 months ago, myself and Reed proved that if you have an important thing to note, that if a measure is invariant, it's stationary with respect to any measure in G you choose. So invariance is like super duper stationary. Okay, so we proved that if you have a stationary action of a hyperbolic group, almost every stabilizer is either the identity or it's at least, something which is hard to define, but like something that depends on the group, in some number. So it's 1/2 asymptotic entropy times the drift. So, what's entropy in drift? So I will just write some formula in the board. So the entropy, the asymptotic entropy measures the rate at which complexities of convolutions of these random walks grow. So this formula maybe is not supposed to make much sense if it's the first time you see it, but it's called entropy, so it must be cool. And drift. So the drift it's the average amount of that if you take n steps of the random walk, that your distance increases in one step. Okay, and this is all well defined. And so to prove this, we replace these horrible ergodic theorems by some abstract nonsense that's true for like random walks in any groups that I could explain if I had 10 extra minutes, but it's it's easy instead of hard, which is good. And so, okay. So it turns out that for any measure mu on any group, this H over L is less than the growth rate. This is called the magic formula, sometimes attributed to Gershik, sometimes to Guivard. And okay, when G is hyperbolic, there's like some measures on G such that this limit is realized. So we can recover our theorem, at least a non-strict version of this. Okay, so one problem is to make this strict. We don't know how to do this. Maybe someone, some student can. But these techniques are sort of very soft and possible to generalize to naturally last slide, to generalize beyond hyperbolic groups. So things like relatively hyperbolic groups, also groups acting on K0 cube complexes, mapping class groups. So lots of other things because sort of in the last few years, myself and co-authors have developed like probabilistic and dynamical techniques that should be sufficient to attack this by now. And this like thing with stationary reactions is so stationary reactions of groups and their stabilizers have become like a giant field in the last few years. So there's lots of other questions there that haven't been studied much that I think should. Do I have negative time?
You have 2 minutes.
Okay. So something else I like thinking about, which is related, notions of genericity of groups. So suppose you have a finitely generated group, and you have a metric on it. So it can be a metric coming from the kilogram, or your favorite Luxembourgian metric. Okay, so you have two notions of genericity in it. One is sort of geometric, one is sort of probabilistic. So the geometric notion, a subset is generic with respect to a metric if like you look at a subset A, you look at the proportion of ball of radius R, which finds the subset A as a proportion of the total ball of radius R. Hopefully it's a proper metric, but otherwise we can't say much. And this should go to 1. Okay, so there's also a probabilistic measure of notion of genericity. So you choose a probability measure of G, and this gives you a Markov chain where your jumps are distributed according to G, according to mu. And a subset is said to be generic with respect to mu if the convolution of mu assigned to the subset converges to 1. In other words, if you take like a bunch of steps of this Markov chain, you're probably going to land in A. Okay, so both notions of the genericity strongly depend on G and mu. So one question that I have wondered a lot is there some relation between the two? Or can you say there is no relation between the two? So in hyperbolic group, Tanaka answered this question negatively when G is a word metric. So it shows that for any epsilon, there's a subset at which you will land with high probability, but which contains an exponentially small proportion of the ball. So I think the time is right to generalize it to a bunch more groups. Okay, and this is all, I have negative time, so okay, this is all related to lots of ergodic theory, and you construct like geodesic flows and groups. Okay, that's a crazy, like, what does it mean, geodesic flow in groups? But okay, it actually means something. And it relies, also it's related to singularity of certain measures on boundaries, and Hausdorff dimension of these measures. And okay, if you're interested, talk to me. And yeah, you can see these slides. Yeah, there's like more stuff there.
Go ahead, you can take a bit more time. Go ahead, take some more time.
Okay. Okay. So maybe there's another kind of circle of problems I wanted to talk about. So if you have a negatively curved manifold, and you have a random walk on its fundamental group. So trajectories, almost every trajectory of this random walk converges to some point in the boundary. And so there is a measure mu, which describes, so mu of A, it's like probability of converging to something in A. So it's called the stationary measure. And if you know something about unit tangent bundles of universal covers of negatively curved manifolds, so the universal tangent bundle of it is like boundary cross boundary minus diagonal cross R. Because the geodesic is determined, so unit tangent bundle, think of it as like the space of unit speed parameterized geodesics, and the geodesic, it came from somewhere on the boundary, it's going to somewhere on the boundary, and it's somewhere along this line at the present time. So that's basically the parameterization. Okay, so this, by taking like mu times dt and fudging it a bit, you can get a measure on this unit tangent bundle of X. And if you quotient out by like some discrete group of isometries, you have a measure on the unit tangent bundle with quotient manifold. And so I proved that if this quotient manifold has finite volume, or in fact is geometrically finite, this measure, so this is a finite measure in the unit tangent bundle of the quotient, and the geodesics satisfy interesting distribution properties with respect to this measure, but this measure is singular to sort of the usual types of measure you study at the unit tangent bundle. The Begg measure, or the measure of maximal entropy. So more generally, the things called Gibbs measures. Okay, so it's interesting, at least to me, to study sort of the affine approximation target properties with respect to this measure that have been studied with respect to other measures. So what do I mean? So maybe you have a finite volume negatively curved manifold, and it's not co-compact, so it has a cusp, so it looks something like this. And okay, you have this measure on it that I'm interested in, chromatic invariant measure on this unit tangent bundle. Okay, so now you pick a geodesic. So you pick like a cusp here. So maybe everything where the injectivity radius is less than something. And you pick a geodesic. So most geodesics, of course, by any kind of ergodicity are going to go in and out of this cusp and et cetera, et cetera. So you take a geodesic, you flow it for time t, and you look at like the longest excursion that it's had into this cusp. And so typical excursions are going to be different with respect to different measures. So it turns out, so by what some people know, Sullivan and constant negative Sullivan and Personsky-Polan in different settings, that n of t, this longest excursion, is asymptotic to log t for almost every geodesic gamma. Actually, some of the problems that Eric's mentioned in this talk could be rephrased in this sense, because if you look at the geodesic flow on the modular surface, then like excursions into the cusp are related to continued fractions. Okay, so something we do know, well, at least I know, is that if you look with respect to the harmonic measure, which is singular with respect to all these measures, geodesics spend less time in the cusp. Typical geodesics spend less time in the cusp than with respect to these more familiar measures. And a conjecture that I made based on like assuming, okay, a bunch of things are by pretending I'm a physicist, I guess, and that everything is independent, is that for almost every geodesic with respect to this harmonic invariant measure, n of t is asymptotic not to log, but to log. And okay, I have some heuristics on how to prove it. So, I think this is a good problem for like a student who, well, yeah. I mean, this isn't like a sure thing, but I think it would be an interesting thing, which is, I think, somewhat accessible. Okay.